Ionic bonding. Remember, we stated that we have two different types of bonding, ionic bonding and covalent bonding. How do we determine if something is ionic bonding? Think all the way back to last week. How did we determine what type of bonding we were dealing with? Parker? Yeah, well, we're on it. We're on it right there. Two elements, whatever that number is. What is that number?
Well, it's the number,
The electronegativity. And remember, we had different ranges of electronegativity. If it was 0 to 0.3, it was nonpolar covalent. Okay? If it was between 0.3 and 1.6, it was polar covalent. The gray area was 1.6 and between 1.6 and 2.1, where it could be polar covalent or ionic, depending on what elements you were dealing with. And finally, just to review, finally, greater than 2.1 was ionic. Now, so we're checking these electronegativities to see what type of bonds are occurring. The most familiar for us, okay, the standard example of an ionic bond is sodium chloride. Go ahead and take out your periodic tables too, please. Now, if I were going to deal with sodium and chlorine, and now we're going to write the dot notation of sodium, it would be so. If I would write the dot notation of chlorine, it would be so. Chlorine has 7 valence electrons. It is a halogen. Sodium has 1 valence electron. It is an alkali metal. Now, if I'm looking up here, I can see that in order to obtain a full octet, that chlorine only needs to have 1 electron to obtain its full octet. Sodium has this 1 valence electron. What's the shell under that 1 valence electron? The shell under that 1 valence electron has 8 electrons already on it. So, does it make sense that sodium wants to give away its electron? Yes, because there's a full shell under it. Does it make sense that chlorine wants to gain 1 electron to have a full shell? Yes. So, actually, what's going to happen is sodium is going to lose that electron. Sodium is going to lose that electron, transfer it over to the chlorine. Once it does so, I have a net charge now of +1. What is the net charge of chlorine going to be? -1. Now, the whole idea behind the ionic bond is they form ions, and then those ions are attracted to each other. Opposite charges attract. Pluses and minuses go together. So, what we're going to actually be seeing occurring, okay, this is just a little idea I showed you with the dot notations. Let me switch to my next slide here. And here you see what actually has happened with 8 valence electrons now around sodium. Sodium still has 11 protons in the nucleus, but it only has 10 electrons, so it's a +1 charge. Chlorine has 17 protons, but now, since it has gained that 1 electron from sodium, it has 18 electrons. Opposite charges attract. That is sodium chloride. So, what is an ionic compound? An ionic compound is composed of positive and negative ions that are combined so that the number of positives are equal to the number of negatives. Just another real quick review, because we're going to see these and discuss these all the time. What is a positive ion called? A cation. What is a negative ion called? An anion. So, the cations, the number of cations, positive charges, are equal to the number of anions, negative charges. Here's just another terminology, some terminology to get down, a definition, a formula unit. Now, a formula unit is the simplest collection of atoms from which an ionic compound's formula can be established. So basically, if we have ionic bonding occurring, we call that compound a formula unit. You're going to need to know that terminology later on when we're discussing different molar conversions. So if something is ionically bonded, we call it a formula unit. It says right here, the formula unit for calcium chloride is CaCl2. Now, we're going to go in and discuss that part of this a little bit. CaCl2. Let's draw the dot notation for calcium. What is it? What's the dot notation for calcium? John? 2 electrons. Going to be on the 1 and 2 spot, right? Now, once again, we've been working with this guy, chlorine. We know chlorine has 7 valence electrons. And we hit this a little bit earlier. Now, what's going to happen for these 2 atoms to achieve their stability? Well, if calcium gives up an electron to that chlorine now has filled its outermost energy level. But what about calcium? Has calcium done any good? Has calcium reached stability? No, he's still got that 1 electron, right? So, does it make sense that there's just another chlorine? That takes the 2nd electron? So what's calcium's charge going to be now? 2 plus. Okay? Calcium, let's see, calcium originally had 20 electrons. Now he's down to only 18 electrons, still has 20 protons. So does it make sense, looking at this, looking at these dot structures, does it make sense as to why we have this right here, CaCl2? Why do we have Cl2? Because in order to balance out the charges, we need to have 2 chlorine atoms for every 1 calcium atom. So it's a 2-to-1 ratio, chlorine to calcium. So when we look at it like this, when I show you the diagrams, I have 2 chlorines. They have each gained 1 electron. I have the calcium that has lost 2 electrons. Therefore, when I write the formula, and we call that the formula unit is CaCl2. Once again, the electron dot notation, I already showed you this, so I'm not going to go over it again for you. But the electron dot notation can be used to demonstrate the changes. I've already showed you this one. Can you draw the dot notations for this one and tell me what the formula unit would be? Go ahead and try it. Draw the dot notations for these two. Okay, if I'm drawing, once again, we dealt with calcium. I probably should have put a different one on here, but what the heck. Here's calcium. Fluorine. Fluorine's another halogen, right? How many valence? 7. So how is this going to bond? Yes, it's going to be CaF2 because we're going to need to have 2 places to gain 1 electron. So calcium's going to give 2 electrons there. Calcium now is going to become, once again, a 2+ charge. Each fluorine is going to have 1 more electron than it originally had. Okay, so we're going to have CaF2. Yes, sir. +2, 2+. Would I count it wrong if it was +2, 2+? I can't think of right now why, but there's a reason why we do +2, 2+ instead of +2. Okay, let me think on that. But I probably wouldn't count it wrong. Okay, but there's a reason, there's a rhyme and a reason why we do it. I just can't think of off the top of my head why that is. All right, now this next one here is going to be a little bit more challenging for you. It's going to be a little bit more challenging, but think it through. Think it through, see if you can do it. Erase these first. It's a little more challenging. Think it through, see if you can do it. Tell me what you got. This one is a little bit more challenging. Let's look at aluminum. How many valence electrons does aluminum have? 3. So when I draw my dot notation, I'm going to have my 3. Oxygen Okay, how many valence electrons does oxygen have? 6. So, how many openings does oxygen have that it wants to fill? 2. How many does aluminum want to give up? 3. Why does aluminum want to give up instead of receive? Okay, easier to give away 3 than to receive 5. Okay, so can you see we got a little bit of a problem here? Okay, a little bit of a problem. Well, what's going to happen? Anybody got any idea what happens here? Lauren, you got one? Yeah, you just keep going until it equals out. Okay? That's how it's going to happen. So, if I would put 2 right there, that oxygen's happy, but now I still got 1 left on aluminum, right? Well, in order to get another, okay, I'm not just going to add a new element in here. So I'm going to just bring another oxygen. And if I would do so, and I get rid of that electron right there, he's okay, but now that oxygen's short. So he's knocked off balance. So then if I get another aluminum, okay, we're going to help out that by putting that right there. Now we're okay with those oxygens. And as you can see, hopefully, if I have one more oxygen, then that could use up those other 2 electrons that aluminum has. So what's the charge of each one of these aluminums going to be? 3 plus, right? Because they've given up 3 electrons. What are each one of these oxygens going to be? Now, when I add up my charges, are my charges equal? Are my charges equal? I have 3 plus and 3 plus is 6 plus. 2 minus 2 minus 2 minus equals 6 minus, right? So my charges are going to be equal there. Now, in terms of ions, we're just dealing with these ions, okay? And ions are positives and negative charges, right? What? If I were to ask you what the sulfur ion is, what charge would the sulfur ion have? Yeah. It would be negative, but there we go. Negative, your negative is correct. It's going to be an anion, but it's going to be a 2 minus. Why is sulfur ion going to be a 2 minus? Yeah, go ahead. It has 6 valence electrons. If you would draw the dot notation, it would look much like the oxygen one just did, right? Okay, so I can just look at that and say, okay, sulfur, let me look on my periodic table. How many does it need? Okay, how many does it need? Let's look at something else. Let's look at Magnesium. What's the charge for magnesium going to be? How do we get 2 plus? It's got 2 valence electrons, so it's going to give 2 away, right? It's going to give 2 away. What about phosphorus? What's phosphorus going to be as an ion? Phosphorus is going to be 3 minus, so we would call that the phosphide. Okay? That's a little bit more than I wanted to do today discussion-wise, but it makes sense to talk a little bit about it right now. Makes sense to talk a little bit about it because if you think of the dot notations of these things, don't these make sense of the charges? Okay? The dot notations should make sense to you when you see the charges. Ions will minimize their potential energy by combining into an orderly arrangement that we call a crystal lattice. When I switch to my next slide, here is a crystal lattice of sodium and chlorine ions. So if you look, okay, the sodiums are the red. As you can see that the reds are always surrounded by blues. So we're alternating red, blue, red, blue, red, blue, red, blue, no matter what way you look at it. Okay? That is the orderly arrangement of a crystal lattice. Okay? A crystal lattice. And finally, the force that is holding the ions together is overall a very strong attraction because we're dealing with positive and negative charges. The positive and negative charges are attracting each other. The overall, that is a very strong attraction. Now, covalent bonds. Okay? Covalent bonds also have a strong attraction. However, the attraction, the forces between the molecules in covalent bonding are much weaker than the forces between the atoms in ionic bonding. So ionic bonds are much stronger than covalent bonds. Okay, so in the hierarchy of bonding, ionic is stronger than the covalent. Now, the final thing we're going to talk about is just a final overview of ionic bonding. Okay? A final overview of ionic bonding. Well, what type of players are involved in ionic bonding? We need to have a metal and a nonmetal. A metal and a nonmetal. Why do we need to have a metal and a nonmetal when we're dealing with ionic bonding? Can anybody explain that to me? Why do we need to have a metal and a nonmetal? Any ideas? Well, stop and think about it this way. Who wants to give up electrons? The metals, right? Do the nonmetals want to give up electrons? No. If I would have two nonmetals together, would either one of them want to give up electrons? No, because they're closer to the 8. So when we have ionic bonding, we need to have somebody that wants to give up electrons as well as somebody who wants to receive. That's why we deal with a metal and a nonmetal. Well, when we form ions, metals form cations, nonmetals form anions. So the bonding is between a metal and a nonmetal, consisting of cations and anions. And finally, anything that is ionically bonded together, anything that is ionically bonded together, we give the generalized term of a salt. A salt. Now, typically people think of, oh, salt, sodium chloride. Okay? But by definition, anything that is ionically bonded would be a salt. So when we were talking about calcium chloride, would that be a salt? Was it ionically bonded? When we talked about aluminum oxide, was that ionically bonded together? So could we classify that as a general term, a salt? Absolutely. Okay? Okay, so these things are the important ones to remember. Ionic bonding is between a metal and a nonmetal dealing with cations and anions, and the generalized term we use is we call them a salt.